All right, math 21. I have no idea what day it is. I'm done writing down what day it is. I can figure it out later. This is chapter 7. We are doing chapter 7 is on the normal probability distribution. We'll be doing 7.1 and 7.2 today. 7.3 will be after the midterm, which is next Tuesday. On Thursday, I'll be going over it. It'll be on my math lab, but you need to be in here to do it. And the review is on math lab also. So there's a review. We're going to go over the review on Thursday. I'll walk you through how I would do all the problems. The midterm is shorter than the review. There's more problems on the review than the actual midterm. But they're the same type of problems. So if you know how to do the problems on the review, you'll be good to go. As I was coerced feels like the right word, tricked into offering the notes. You're free to use your notes on the exam. I don't know why I ever really fighted that much in stats. Usually the only ones that do well with their notes were the ones that were going to do well without their notes. Generally, the student that is not going to do well wasn't taking notes anyway, so offering them to use their notes doesn't do anything. Which is interesting that it tends to be the case. But we'll do chapter 7 today. I think what you're going to care about is doing how to do this in StatCrunch. We're going to do stats, calculators, normal. This is the section that has the shitty fucking charts and tables and all sorts of shit if you did it by hand, if you ever learned to do it by hand. Like the tables in this thing, there's like fucking 4, 5, 6 columns on each page. There's like fucking 50 lines, rows on each page, and there's like 4 or 5 pages. And that was how we used to do it before computers. If you're doing that and you choose to do that rather than StatCrunch, Godspeed. I hope you pass. I recommend using the computer. The computer does all the work for you. Don't be stubborn. Learn to use some software. Okay? So we are looking at the normal distribution. Great thing about it is bell-shaped. This green pen sucks. Let's scrap it for a better green pen. What does this mean for us? The area beneath the curve equals 1. Or 1.00 if you like to look at it that way. So this causes us to have specific areas under the curve give us P of X, our probability of X. And that's what we're going to be talking about today. B. The normal distribution function is a graph. Not a graph, it's fucking symmetric. That's what I wanted to say. Of course it's a graph. Normal distribution. It's a little 5 minutes into lecture. It's a little early to be fucking dissing out. And we've seen these bell curves. Like the bell curves, the bottom increases from left to right. That axis on the bottom which I'll call the x-axis, increases from left to right. We've seen this on all of our bell curves. When we did the empirical rule, I use the same color and those are all really fucking close to each other. So let me put little fucking lines between them so you can see them a little bit better. Finally, the graph never touches that bottom axis. It gets close, but it never actually touches it. You guys ready for more? Just giggle every fucking time. You love it. You're a sick fuck. You know that, right?
Yes.
You just giggle and laugh every time. You know that's encouraging,
I
right?
have to laugh like I'm crazy.
It's just encouraging me. All right. So I said that the specific area under the curve is P of X. There's a little more to it. I'm gonna like draw a quick picture and give you like what I mean a little bit further. So we got a bell curve. And without like labeling any points on the graph, let's say we're looking at this region right here. So for a given area under the curve, or specific area under the curve, area or region, we can say two things. A, this represents the proportion of the population who possess the trait. That's one option. The other option is if we randomly select an individual from the population, it represents the probability that person possesses the trait. And maybe not necessarily person, but the individual. It may not be a person, it may be like a car or something like that. That the individual possesses the trait. Good thing about it, the homework will usually tell you that it's just homework will inform you this is a normal distribution. They'll say it one or two ways. They could say the data is normally distributed. Or B, the data follows a normal distribution. I'm telling you both because for the longest time, I just assumed students would recognize that if you see normally distributed, it means normal distribution. And not every student made that connection. So it says it two ways. This tells you that it's following, or that they used a normal probability distribution function to do all this stuff. You guys ready for more? Nope. I see a couple people still writing. Say your fucking name. Did I tell you what Beta, did I tell you about my grad teacher, my grad advisor? So he was from England and he made fun of us for saying Z rather than Z. Every other country says Z. We say Z because it's fucking person that wrote the alphabet song didn't like that Z didn't rhyme with fucking V. So, or Z didn't rhyme with V, so he just changed it to Z. And so us Americans call Z, and he kept calling us stupid Americans every time we say Z, because we would use X, Y, and Z a lot in mathematics. Well, we also use a lot of Greek letters, alpha and beta, and he would say beta. It's very common to say beta. They even had the Betamax for like the original old school VCR. It's called the Betamax. He would say beta. We all said beta. Except in my group, we had a student that was Greek. And so after he said, "You stupid Americans," one time, the next time he said beta, she said, you stupid English people, it's beta. No, he would say beta, it's beta. Like alphabet, beta, alpha, beta. So that's why I like the name beta. That's why every time, once in a while, I'll play it just out of nowhere. Because you remind me of it. And it makes me laugh at him. I like him. All right. So let's take a look at this in StatCrunch. We're going to give an example real quick. IQ test, we've talked about this before. It has a mean of 100 and a standard deviation of 15. We'll look at the range. Let's look at 85. $85 to $115. So if we did a empirical rule, this is plus or minus 1 deviation. Get to 85 and 115. And plus or minus 1 deviation tells us that this was 68%. That's how we learned the empirical rule. It's really just a close approximation, as we're about to see. It's important to know before we go on to this next thing, for continuous distributions, like the normal distribution, the probability that X actually equals a specific value is 0. It's area, and if it's just a single value, it's a line. It has no width. And area is length times width. So it's got no width. A specific, just one single number has no value. So we look at ranges of numbers in this normal distribution. Which means like anything that, like if we have probability that X is less than 6 or 2, let's go 2, it's going to have the exact same value as the probability that X is less than or equal to 2. Because the equal portion is 0. So StatCrunch only gives us 2 options. It only gives us we can choose less than or equal to or greater than or equal to. Those are our only choices. Because less than or equal to is the same thing as less than, and greater than or equal to is the same thing as greater than. Okay, so let's go look at this in StatCrunch. Sign in real quick while people finish writing it.
What does it say to the left of the arrow of 68%? The standard deviation symbol.
It should say plus or minus one deviation. You're right, it looks
I'm
sloppy.
I've been paying attention.
All right. So we're gonna go stats, calculators, normal. I'll make a note of this in just a second, because this, notice it starts with a mean of 0 and a standard deviation of 1. This is the z-score setup. So this is called the standard normal distribution. That's 7.2. Anytime the mean is not 0 and the standard deviation is not 1, we just change it. And I wanted between, and I'm gonna say 85 and 115. And notice it says 0.68268. So the probability of being between 85 and 115 is 0.68. We'll go 27, 4 decimal places, which is 68.27%. Not exactly 68. So I got this written down over here. The empirical rule is just a rule of thumb. When accuracy is not important. And we can only use it for like whole numbers of deviations. It doesn't help me if I have 1.5 deviations. It only helps me if I have 1, 2, or 3 deviations, right? That's what the empirical rule plots out those, and we have a percentages based on that. So like for most things, if it's important, like it's your job, you probably shouldn't use the empirical rule. But it's close. It's fairly close, but not spot on. But calculating the normal distribution is much more accurate. And the way you had to do this by hand is everything was in z-scores. So you had to convert everything to a z-score and then use these z-score tables. It was god-awful miserable. A little more we can pull from that. That 68.27 tells us 2 things. I'm going to do this for several of a lot of these examples until like sinks in. There's 2 things this means. A, the proportion of the population with an IQ between 85 and 115 is 68.27%. Or B, the probability that a randomly selected individual from the population possesses the trait, or, and to be more specific, has an IQ between 85 and 115. Is 68.27%. So there was something neat on the calculator. I want to show it to you again real quick. We're going to use it a bunch, but like when I start off with a blank calculator, I had the mean was 0, standard deviation was 1, and I only had 2 options up here. As soon as I changed these options and clicked compute or one of these buttons, this appeared, the 68, 95, 99.7. We can look at the bottom and it's doing increments of 20, even though the standard deviation is 15. If you want to see the empirical table, the empirical rule format really quickly, you can click on it and see it. It'll shift the bottom row to look like that. So it now has spacing of 15. It's a handy little like side feature of it. Okay. Any questions on that? We're going to do some more examples. Now, just because I said we don't want to use the empirical rule doesn't mean that that graph isn't useful. So like, let's take a look at this. The weight of giraffes is normally distributed with a mean weight of 2,200 pounds and standard deviation of 200 pounds. First thing we're going to do is draw this distribution with the 68, 95, 90, 99.7 tick marks. So we have 2,200 in the middle. And we're adding 200 as we go up. And we're subtracting 200 as we go down. Okay, and now second thing, we're gonna use that graph. But I don't have any room to write the next part. Shade the area, this is part B. Shade the area to the right of 1900. What does this mean? So the first things first, we gotta like identify where 1900 is. 1900 is between 1800 and 2000, it's about halfway. You're still fucking squinting. Why don't you move up? Knothead. That's what my mama used to tell me when I was doing something silly. So that's 1900, and I want to shade the region to the right of it. What does it represent? So let me bring that like the description of the problem back down, because that kind of like helps us. What are these numbers even referring to along the bottom? They're the deviations, but the numbers themselves are weights. They're weights of giraffes. What are the numbers to the right of the 1900 in relationship to the 1900? They're heavier weights. Higher weights or heavier weights. So this is representing the proportion of giraffes with that are heavier than 1,900 pounds. LBS is the abbreviation for pounds. I have no idea why. That's actually the first interpretation. What else can I say? We could say, talk about the ones that are less than it, but we want to specifically talk about the shading. I said it's the proportion of giraffes that are heavier. What did I do in the previous examples? What was the other description I gave? Huh?
So like the ones that. The ones that weigh less, don't. 1,900.
That's kind of like what he was saying. That's talking about the unshaded region. Not where I was going.
Have to do with the inequality signals or symbols?
Oh, yeah, same way the heavier had to deal with it.
There's a cap at a certain weight you can't pass.
No, it actually doesn't show the cap. We don't know what the cap is. There's gotta be a cap. Right? There's gotta be a cap, but we don't know what it is. This graph actually gets closer and closer to zero, where it's like you would need a microscope to like see the difference, the space. But to the naked eye, it's like it does, you might as well say it's hitting the line. Where I was going for it was, this is talking about the proportion of giraffes, but if we select a random giraffe. We're talking about that, the probability that this giraffe is heavier than 1,900 pounds. Or weighs more than 1,900 pounds. Is that area. We've done this several times throughout the semester, actually. A is related to the relative frequency. And B is the probability of a pick in the future. So relative frequency is past information. And B is the probability that we get something like it in the future. We talked about this at the beginning of chapter 5, because I was showing you how to get probability, and they look exactly the same as relative frequency. Because they're related, they're definitely related. They're like twins, just slightly different. You guys ready for more? Let's go look at it. Let's see what it is on StatCrunch. So again, you do stats, calculators, normal. Stats, calculators, normal. I'll just change the one that had the 100. And we had 2200 and 200. And we wanted greater than 1900. So there's a good chance. 0.933 is 93.3%. Most giraffes weigh more than that. I'm assuming that those numbers are related to adult giraffes. Okay, so notice, like, even if wow. Why is it not showing me? Let me put this back at 0. Why is it not showing me? The fuck? Let me put it over here. It won't do the bit, it won't do. Oh, it's already done it. It already set it up to have the bottom row look that way. I was like, where's my 68, 95, 99.7? There's no button here. They automatically did it. Notice that if I do greater than 1900, like I am between deviation marks. So I couldn't use the empirical rule here at all. Okay. So I can't use the empirical rule at all. Let's say we wanted to compare to like another large animal. I think elephant's way too large. Let's go like hippo. Compare to a hippo. I don't have any data on a hippo. The real reason I'm bringing this up is like if we want to compare things that are different, we have to convert to a z-score. To compare to a giraffe, we need to do z-scores. So our formula was x equals mu plus z sigma. And if you solve for z, you get z equals x minus mu over sigma. We did this before. When you do this, z scores have a mean of 0 and a standard deviation of 1. Everything we've been doing so far has been normal distributions. This is called the standard normal distribution. So if you see it say standard normal distribution, the standard normal is implying this right here. Let's do that giraffe real quick. As just a refresher. The z-score for the giraffe for a 1900 pound giraffe, 1,900 pound giraffe. It had a mean of 2,200 and a standard deviation of 200. And the 1,900 is the X. So we have Z equals X minus mu over sigma, which is 1,900 minus 2,200 over 200. This is negative 300 over 200, which is negative 1.5. And that'll end 7.1. Let's take a 5-minute break to let people go to the bathroom or something like that. I'll pause the video real quick.